Let's look at an example for drawing a Lewis structure of a compound that requires a double covalent bond. Carbon dioxide, CO2. The first step is to determine the number of valence electrons. There is one carbon atom. Carbon has 4 valence electrons. There are 2 oxygen atoms, each of them having 6 valence electrons. This gives us a total of 16 electrons in our Lewis structure. First, we put the least electronegative element in the middle, the carbon, and we attach it by single covalent bond to each oxygen atom. Each of these covalent bonds is 2 electrons, so a total of 4. 16 minus 4 means that we have 12 electrons remaining, which we will place as 6 pairs on the oxygen atoms to give each a total of 8, which you see below. 2, 4, 6, and then remember this also counts as 2, so this oxygen has 8. Mirror image on the other side, 2, 4, 6, 8. Okay. As a check, we had 16 electrons to work with. We have used all 16. Carbon, however, does not have enough electrons to complete its shell. Looking at that central atom, right now, carbon only has 4 electrons, and it needs 8 to be stable. We must form double bonds between carbon and oxygen in order to make the carbon stable. So you can see that demonstrated by the arrows moving a pair of electrons from each oxygen. That way each oxygen continues to have 8, and the carbon also has 8. So instead of sharing only one pair, the double bond that you see shares 2 pairs of electrons. One pair is taken from each atom and replaced with another bond. So now carbon has 4 bonds, which is a total of 8 electrons. Each oxygen has 2 bonds and 2 lone pairs, so that they also each have 8 electrons. Okay, let's continue our practice of drawing Lewis structures with multiple bonds using oxygen. O2. So oxygen has 6 valence electrons, and there are 2 oxygen atoms for a total of 12 electrons in this Lewis structure. There's no central atom here. There's just 2 oxygen atoms connected to one another, like this. That single bond there is 2 electrons used. Okay, which I'm going to go below the box here, leaves us with 10 electrons remaining to draw. Now we start by filling up the octets. And, we generally say the outer atoms, fill those first. Here we just have to pick one. So I'm going to fill up the octet on the right-hand side for this oxygen molecule. 1, 2, 3, 4, 5, 6. And then, of course, these 2 electrons give this oxygen on the right here now has 8. Oh, I did that wrong. How many did I draw? I drew 6. So that leaves me 4 electrons. So I put those 4 electrons on the other oxygen atom. 1, 2, 3, 4. Now I've drawn all the electrons I can draw. The problem is that the oxygen on the left only has 2, 4, 6 electrons, and it needs 8. But I can't just draw another lone pair. That would make too many electrons. So what you do is you move electrons to create a multiple bond. And what we're left with is a double bond between the 2 oxygens, and then each one has 2 lone pairs of electrons. So now both oxygens have 8 electrons in their outer shell, and both are stable. So just pull this so you can see the diagram a little more clearly. Okay, let's have another practice with nitrogen, N2. So each nitrogen atom has 5 valence electrons, and we have 2 of them. So we got to draw a structure that shows 10 electrons total. We connect each nitrogen together by single bond. If I use up 2 electrons in the single bond, again, I'm going to come down here. That leaves me with 8. So I pick one of the atoms and I fill up its outer shell. I give it an octet. So here's 2, 3, 4, 5, 6, 7, 8. Okay, now this nitrogen, oh, that shouldn't be there. This nitrogen on the right has 8 valence electrons. And in green, I drew 6 dots. That leaves me with 2. Now, if I put those on the nitrogen on the left, that's great. I use up all my electrons. But the nitrogen on the left only has 4 electrons. Here's 2 from this lone pair. It's difficult to draw these dots, but here's 2 from the lone pair and 2 from the covalent bond. That's 4. It needs 8. So we've got to move and create some multiple bonds. So this is 2, 4. I'm going to move these 2. That'll give me 6. I'm going to move 2 more. That'll give me 8. So I end up with a structure that looks like this. Remember that moving those electrons creates multiple bonds. So now we have 3 bonds. And then again, if we move these 2 electrons and move these 2, that only leaves us with this lone pair here and here. So now if we count, just to be sure, we have 2, 4, 6. These 6 electrons belong to each nitrogen. So they both have those 6, and then they each have a lone pair to get them to the 8 electrons required to be stable and have a full octet. Let's practice again demonstrating how multiple bonds form with carbon monoxide, CO. So first, determining the total number of valence electrons. There's 1 carbon atom. Carbon has 4 valence electrons. And there's 1 oxygen atom. Oxygen has 6 valence electrons for a total of 10. Then we connect the atoms by single bonds. There's no central atom here because there are only 2 atoms, but it is true that the carbon is less electronegative. Okay, and so with that single bond, we've drawn 2 electrons. So if I subtract, it means I have to draw 8 more. So when we start filling the octet, we start filling from the outer atoms in, or in this case, we'll start with the most electronegative element. So we'll start with the oxygen, and we'll draw, we need 6 more. So 1, 2, 3, 4, 5, 6. Remember that this bond counts for 2, so there's 8 electrons surrounding that oxygen. So we've drawn 6. That leaves us 2. So I need to draw 2 more. So oxygen is full, so I'll come and draw those on carbon. Now, we've used up all of our electrons, but we're not done yet because carbon right now only has 4 electrons, 2 from the bond and 2 from the lone pair. So again, if we run out of electrons, but we don't have a stable octet everywhere, we need to move electrons to form multiple bonds. So it has 2, 4. I'm going to move these 2 to give it 6, and these 2 to give it 8. Our diagram will look something like this. We've still got that lone pair. And then we'll have the carbon, and it'll now have a triple bond for all 6 of those electrons. And then oxygen. And of course, we moved those 2 pairs, so now I just have 1 remaining lone pair. So if I count the total number of electrons, each one of these is 2. So this is 6, 7, 8, 9, 10. So I'm still using my 10 electrons, but each of these atoms has 8. So there are 6 for carbon from the bonds, 6 and then 7, 8. And there are 6 for oxygen from the bonds, and then 7, 8. Everything is stable with 8, and all 10 electrons are used. So that's our final Lewis structure for carbon monoxide. And as a note, the third bond in this structure is something called a coordinate covalent bond, because both of the electrons are contributed from the oxygen atom. You can look up more details on a coordinate covalent bond if you want to, but what it means is that oxygen is just contributing more electrons to this shared pair here than carbon is. Now that we've drawn several of the Lewis structures for these diatomic elements, let's talk about what they are. There are 7 elements in the periodic table that are always diatomic. What that means is, in their elemental state as elements, they always are seen and exist as 2 atoms covalently bonded together. So here's how I remember this. This is the device I've used to teach students in the past. There are 7 elements that start with element number 7. So in your periodic table, nitrogen is atomic number 7. We make a number 7. So nitrogen, oxygen, fluorine, chlorine, bromine, iodine. Now, start at number 7, make a number 7. That gives us only 6 elements. And then we just have to remember the 7th one is hydrogen. Another way I've seen that taught for students to remember, there's this mnemonic device here where we just sound out these letters, and it sounds like this. Honkelbriff. Honkelbriff gives us hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, and fluorine. That's how we remember the 7. Again, they never exist as one single atom. It's always 2 atoms covalently bonded together. So the question is, which of these diatomic elements contains double bond, which contains triple bond? So we actually drew them. We drew the double bond, one that we drew. If you go back several slides to the example, it was oxygen. The triple bond that we drew was nitrogen. All the rest of them, all of these, plus hydrogen, are single bonds.